All right, welcome back. Today we're going to jump into a really fun programming puzzle. Now on the surface, it seems super simple, but it's actually hiding a pretty sneaky challenge. How do you perfectly pack and then unpack a list of strings? It's a great one, so let's get right into it.
So, here's our game plan. First, we'll lay out the puzzle itself. Then, we'll walk right into what I call the delimiter trap. You know, the simple solution that everyone thinks of first and why it fails spectacularly. After that, we'll unveil the hero of our story, the length prefixing fix. We're going to break down exactly how it works, throw some tough cases at it, and then really understand why it's such a brilliant solution.
Okay, so first things first, let's set the stage. The problem we're dealing with here is a classic computer science concept called serialization. And all that really means is, how do you take some data, in our case a list of strings, and squish it down into a single piece of information that you can easily store or send over a network, and then, this is the important part, build it back up perfectly on the other side.
So here's the question, plain and simple. How do you take a bunch of separate strings, combine them into one single string, and then, later on, magically get them all back exactly as they were with no mistakes?
So let's say you have a list like, hello, world. The goal is to find a bulletproof method to turn that into some single encoded string, and then have a decoder that can take that string and hand you back the original hello, world list. No errors, no confusion, just a perfect round trip.
All right, so what's the first thing that pops into your head to solve this? Well, most people's first instinct, and it's a totally logical one, leads them straight into what I call the delimiter trap.
The idea seems pretty obvious, right? You just pick some special character, something you think won't show up in your text, like, say, a hash symbol, hashtag, and you just stick it between all the words. It acts as a little fence, marking where one string ends and the next one starts. Simple. And you know what? For a simple case like hi there, this works like a charm. It becomes hi hash there, and you can just split it on the hash. Easy. But, and this is a huge but, here's where the whole thing just completely falls apart. What if one of your strings already has the delimiter in it? Now, hi hash there becomes hi hash hash there. And, well, we've got a big problem. When you go to decode this, is it hi nothing there, or is it hi hash there? You have no way of knowing. The information is ambiguous, it's broken. And that right there is the fatal flaw. See, the rules of the puzzle say our strings can contain absolutely any character. So there's no such thing as a safe character to use as a separator. Any symbol you pick, no matter how obscure, could be part of the original data. And just like that, the simple delimiter idea is totally out the window. It just doesn't work.
Okay, so this is where a much, much smarter solution comes into play. It's called length prefixing, and it's so elegant because it completely sidesteps that whole ambiguity trap. And the core idea is just brilliant. Instead of making the decoder guess where a string ends, you just tell it up front. For every single string in your list, you prepend its length, followed by a separator like our hashtag, and then you add the string itself. So the format is always length hashtag string.
You can really see the power of this with an example. So the list hello, hi becomes 5 hello, 3 hi. Now think about decoding this. You read the first character, it's a 5. Great, you now know with 100% certainty that you need to grab the next 5 characters. Then you see a 3. Awesome, you grab the next 3 characters. It doesn't matter what those characters are. They could be more numbers, more hashes, anything. You know exactly how many to take. The ambiguity is just gone.
So how does this actually look in code? Let's break down the logic step by step for both the encoding and the decoding parts. Okay, encoding is super straightforward. You basically just loop through your list of strings. For each string you hit, you find its length, you tack that number onto your result, followed by the hashtag separator, and then you tack on the string itself. You just keep doing that, one after another, until you're done with the list.
Decoding is a little more clever. It's kind of like a little dance with a pointer. You start at the very beginning of your big encoded string. First, you read characters until you hit that hashtag symbol. Whatever number you just read, that's the length of the string that's coming up. Okay, then you just hop over the hashtag. Now you know the length. Let's say it was 5. So you just grab the next 5 characters from the string. Boom, that's your first word. Finally, you move your pointer past that word you just grabbed, and you start the whole process over again, right from where you left off. You just repeat that until you hit the end of the string. Now, a truly great algorithm doesn't just work on the easy stuff. It has to handle all the weird, tricky inputs you can throw at it. So let's really put this length prefixing method to the test and see how it holds up against some of the toughest edge cases.
And this is where you see just how robust this system is. What about an empty string? No problem. It just becomes 0 and hash. What about our old enemy, the delimiter inside a string, like a hash b? Easy. It becomes 3 hash ab. The decoder sees the 3, grabs ab, and doesn't even blink. A string made of numbers, like 1, 2, 3, encodes to 3 hash 1, 2, 3. Perfect. And what if you start with an empty list? Well, you just get an empty string back. It handles every single one of these tricky cases flawlessly.
So let's just take a step back and really nail down why this approach works so well. What's the key takeaway here? Well, first and foremost, it is completely unambiguous that length prefix is like a perfect set of instructions. There's zero guesswork. And second, it's really efficient. Both encoding and decoding run in what we call linear time, or O of n, where n is just the total number of characters you're working with. That's a fancy way of saying it scales really, really well. As your data gets bigger, the process time grows in a nice, predictable way. And really, it all boils down to this one simple idea. The delimiter method fails because it forces the decoder to guess where the data boundaries are. But the length prefixing method? It succeeds because the data is self-describing. It literally carries its own instructions with it, which makes decoding simple, reliable, and always correct. And that kind of leaves us with one final thought to chew on. This powerful principle, the idea of embedding metadata, of making data carry its own instructions, is an absolute cornerstone of good, robust system design. I mean, think about things like network packets or file formats, or even APIs. So my question to you is, where else out there in the world of technology can you see this powerful idea of self-description at play? It's everywhere once you start looking.